This is an introduction to equilibrium. Let's take a look at this picture right here. If you notice in the left-hand side of the picture, I have 3 people in this room, and on the right-hand side of the picture, I have 1, 2, 3, 4, 5 people in this room, and then we've got a door that's separating them. There is not the same amount of people, and so if I want to use this analogy and kind of look at it with concentration, this room has a higher concentration than this room. Well, let's just say that these 2 people, or these people are going to start moving. And it's always, let's say, 2 people. So 2 people from here are going to move into the left side room. And 2 people in this room are going to move into the right side of the room. And there's constant movement, constantly. Nobody's ever stopping. 2 will always go there in exchange for 2 going here. So what can we say? Well, even though there's 3 and 5 here, those 3 and 5 will always remain the same. So the amount of people in each room will always remain the same, even though it's not the same total amounts. 3 and 5 don't total each other, but 3 will always remain in this room, and 5 will always remain in this room thanks to the constant exchange. And that constant exchange for us, for equilibrium, means is that we've reached a constant rate. It's the rate at which things are happening. So again, just to kind of summarize that analogy, even though the number of people in each room don't equal each other out, the rate at which they're moving, right, is constant, and it equals out because those concentrations stay the same. The number of people in each room stay the same. Okay? This is what equilibrium is. It's no more changes in concentration because what's happening in the forward direction is equaling what's happening in the reverse. These people move forward, these people move reverse, and it's happening at a constant rate. So to apply this to our chemistry, we have to first remember that on the left-hand side we have reactants, and the right-hand side we have products. And in order to form my products, we have to understand that the products are only made if the reactants somehow collide into each other. And this is a really easy model to understand. It's called the collision model, and it just makes sense. It says reactions occur because molecules or atoms are constantly colliding. In other words, the reactants have to break apart or make new things by collisions, right? So if I have my example seen here, right, if I want to make this final product, what has to happen is these reactants must somehow collide, right, and either break apart or form together. This is the collision theory, is that your reactants are going to constantly come into contact with each other to make my products. Notice the arrows are both forward and reverse. We've got a double arrow happening. And we know from the last chapter that that means that these products seen here are going to detach, right? Again, collide in some sort of a way and reform back into the reactants. The rate at which this is forming equals the rate at which that is happening, right? Vice versa. That is equilibrium. So, just to quickly go back to this picture, right? When the rate of the products being formed equals the rate at which the reactants are being formed, you've reached equilibrium. Well, this takes a little bit of time, right? Because in the beginning you have a lot of reactants, but eventually they're being used to make the products. So this kind of dwindles. Well, then the products, there's so many of them, they can go back and make the reactants. And eventually what happens over time is the exchange starts to even out. And when this exchange is happening at a same rate, not necessarily same amounts of stuff. Remember the people in the room, 3 people always stay, 5 people always stay. You're at equilibrium, okay? So in other words, equilibrium is when the reactants and products are moving back and forth at the same rate, back and forth, okay? I also like to put it this way. It's when the rate of the forward reaction, in other words, reactants forming products, equals the rate of the reverse reaction. Products forming back into the reactants. Okay. Now we like to think that these reactions stop eventually. Like as soon as they're all complete, they stop. Well, that's kind of a lie. In reality, they keep going back and forth and back and forth. The reaction actually never stops. We don't sometimes notice anything happening, maybe like in our beaker or our test tube, but that's because everything's basically happening in one direction, is balancing out with everything happening to the reverse reaction. So it almost appears like we've stopped at some sort of a stability, when in fact we've just reached an equilibrium. Okay? One more thing to remind you about that we've said a few times is that, remember, no more changes in concentration occur at equilibrium. 3 people will always remain 3 people. 5 people will always remain 5 people. 3 is my concentration here, 5 is my concentration here. Are people constantly moving? Yes, but that rate is what's constant. That's equilibrium. Okay, I'm going to also introduce a new variable for you, and that's the variable K. K represents the equilibrium constant. And the equation for K, and how to calculate for K, is you take the concentration of the products and divide them by the concentration of your reactants. And what's really important is if you're using K, always remember that you're at equilibrium. Some other things to remember before we try a practice problem is what the bracket means. The bracket seen here and here means concentration. Another thing to remember is we have a way to measure concentration. In other words, to give a number to concentration. Not just saying a lot or a little, but actually saying a number value. And that's molarity, and we learned that also in our last chapter, represented by capital M. Here's a refresher. Molarity is your moles of solute over your liters of solution. Okay, so how do we actually calculate for this? Let's take a look at a sample generic problem. So I have my equation seen here. A plus B reacts to form C plus 2D. Okay, well if I notice right there, it's a reversible reaction. So this reaction will eventually reach equilibrium, right? Indicated by my double arrow there. Okay, it will not go to completion. So I bring back my formula. My formula says my products go on top. Okay, I like to think of it as P over R, spells PR. If my products are C, then I put the concentration of C there and D in here. Well, what do I do with this 2? That coefficient becomes a power. I raise D to the second power. Any coefficient becomes a power. I attach it to the D because the coefficient is attached to the D here. It represents 2D. How about on the bottom? Well, I just plug in the concentration of A and B. Now, in a real problem, you'll actually be given concentration values in molarity. Don't forget, they must be in molarities because these brackets mean concentration. If they're not in molarity, you need to calculate and figure those out. Okay, let's look at another example. Here we have a real equation, and that is water, liquid, turns into hydrogen and oxygen, both gases. So according to my equilibrium constant equation, right, if I want to figure out my equilibrium constant for this reaction, I have to take the concentration of my products, don't forget these are my products, and put them over my reactants. Okay? Well, there's something that you need to know, and that is certain states of matter are not included in this equilibrium constant. And here they are. Gases and aqueous states of matter are included. Check mark, include them. But if you come across a solid or a liquid in your equation, don't put them into my equilibrium constant. Okay? So let's take a look. Liquid. It does not go into my equilibrium constant. So how do I do this? Well, I've got my 2 products up on the top. They're both gases. Do gases qualify? Yes, they do. Put them in. I have H2 and O2. How about this coefficient? Well, remember, coefficients become the powers. So I take my hydrogen and I raise it to the 2. Now this 2 is because of that 2, not because of the subscripts. Don't worry about the subscripts. They don't play a factor, okay? Now, if you notice I put this division line, but is there anything to divide by? Should I put the concentration of water here raised to the second power? No, because water is a liquid, and if you remember from our rules, we don't put liquids. So how do I write this final equilibrium expression? That's another way of saying it. Here is my equilibrium expression. It is just H2's concentration raised to the second times O2's concentration. That's the equilibrium expression for this balanced equation. Again, notice the subscripts do not become powers. The coefficients do. That's the end of the video.